Hey guys, it's Dora.
And Raha.
And today's video is on
hydrolysis and the pH of solutions.
So welcome everyone. Today we'll investigate the pH of various solutions due to the hydrolysis of various compounds. Let's start with something that doesn't involve hydrolysis. Nice and simple. This is a solution here of 1.75 molar magnesium bromide. So we think this solution will be neutral because when magnesium bromide comes apart, you get the magnesium 2+ ion and these bromide ions. If you look here, the bromide ion is the conjugate base of a strong acid, hydrobromic acid, and consequently, since this reaction here only goes forwards, all the strong acids are like this, the reaction only goes forwards towards the ions and not back towards the acid, forwards only, then we don't expect bromide ion to do any hydrolysis, and magnesium ion we know also to be neutral. So neither one of these are acid or base, and this solution has a pH of 7. Let's look at our next solution. This one is nitric acid, a strong acid, we know that, and here is the strong dissociation for nitric acid. Notice there's no equilibrium here, it's just a straightforward stoichiometric dissociation. And the pH is a negative log of the hydride ion concentration, which will be in our case the negative log of 0.050 or 1.30. Notice that in 1.30 there are two significant figures because in a logarithm only the values after the decimal place are significant. So there we go. 5.0 by 10 to the 2 has 3 values in it, and 1.30 has 3 values in it, two significant figures. Let's look at our third example here. This is barium hydroxide. That's a strong base, barium hydroxide, and we expect it to have a high pH. Here's a dissociation reaction for barium hydroxide. Notice there are 2 hydroxide ions for every 1 barium hydroxide that comes apart, and its concentration will be 2/1 times the 0.0050 of the initial concentration. Here we have the pH equal 14 minus the pOH, and that is 14 minus a negative log of 0.0100, and this gets you a pH of 12. Indeed, barium hydroxide is basic. Let's look at oxalic acid now. This is a weak acid, and we expect it to have a low pH. Let's look up oxalic acid. It's one of the stronger weak acids found here on the acid-base table, and you can see its Ka value of 5.9 by 10 to the whatever it is. Anyway, 5.9 by 10 to the minus 2. Here's the dissociation reaction. It's an equilibrium reaction, mind you now, for oxalic acid. It makes the hydride ion and the hydrogen oxide ion. We use a nice table, put in the initial concentrations here, a shift of plus x to the right, minus x to the left, and we have these final concentrations 1.30 minus x and x on the right-hand side. So here's the Ka expression, written the same way you'd write any K expression, and we have x squared over 1.30 minus x. Now let's talk about the simplifying assumption that so many of you are so used to seeing. And in this case, we'll look at the concentration to K value and realize that there's not quite 2 orders of magnitude here. We're looking for 4 orders of magnitude if we want to make that simplifying assumption. So we'll solve this one with our calculator, and we'll graph K, Q, and Q there, put our 2 expressions in, and go ahead and get them here. We'll talk a little bit more about this process later on if you like, but just making it quick for now, we get that x equals 0.249 when you graph intersect to these guys. That gets you the pH as a negative log of 0.249, and that negative log is 0.60. So really, truly quite an acidic solution. Let's look at hydrogen oxalate. This we expect to be a weak base, the pH greater than 7. The reason is because when hydrogen oxalate dissociates in water like this, releasing the sodium ions and the oxalate ions, sodium oxalate dissociates in water, the oxalate ion C2O4 2- can then make a weak acid or weak base, in this case it's a weak base equilibrium with water. And you can see it'll get water's proton there and make the hydrogen oxalate ion. Notice that this ion we were just looking at before, that's not the oxalate ion, that's the hydrogen oxalate ion. So to see oxalate ion acting as a base, you have to go down and find it on the right-hand side of the table. You see it's the conjugate base of the hydrogen oxalate ion. So here we have the oxalate ion. It's going to act moving to the left here, forming the hydrogen oxalate ion. In other words, oxalate ion here is going to act as a weak base. We will need to compute its Kb. Here we have the Ka of its conjugate acid, which is the hydrogen oxalate ion. Remember, conjugate acid and base differ by a proton. So here we are, back to our problem. We know that we'll get Kb as Kw over Ka, and if you've forgotten that, so quickly remember that Ka times Kb equal Kw for that conjugate acid to conjugate base pair. So here we have the Kb, it will be Kw divided by Ka, and the Ka, of course, is the Ka of the conjugate acid, namely the hydrogen oxalate ion. Okay? Kw 1.0 by 10 to the minus 14, Ka 6.4 by 10 to the minus 5. We got that from the table. And here we have the Kb for this as 1.56 by 10 to the minus 10. That's the Kb for our oxalate ion. It's a quite weak base. So again, we'll have the ice table. It's the same, just use your imagination if you like. And you get here, we'll get the x squared over 1.30 minus x. And in this case here, I would suggest that it's probably okay to use this simplifying assumption. X will be a lot smaller than 1.30, so that 1.30 minus x will just still be 1.30. The reason we're making that assertion is that there are 11 orders of magnitude between the concentration and the Kb. Remember, any more than 4 orders of magnitude between the concentration and the K value, and we're usually good to make this simplifying assumption. So there's 11 orders of magnitude here, so we'll be more than good. And the Kb value here is 1.56 by 10 to the minus 10. And we'll just do algebra here to solve this. And take the square root, and we wind up with 1.43 by 10 to the minus 5 molar for the hydroxide ion concentration. pH is 14 minus the pOH, which is 14 minus the negative log of, etc., as we discussed already many times. And you get here a pH of 9.15. So stay tuned for part 2 of this short video series here, hydrolysis and pH of solutions, when we get into a little bit more complicated situations.
This is my dad's YouTube channel. It's awesome. So like, comment, and subscribe!